Hello. Can anyone text me in my, chat box if I am audible? Okay. Uh, okay, I'll start the meeting. Mm. Sure. I hope the screen is visible. A PowerPoint I have shared. Yeah. So let's start the class. Uh, Whenever the screen, my screen stopped being shared, please write in the message. I guess the screen is shared. If anyone can write yes or not. Mm. Yeah, thank you. Okay. So, in this class, we'll discuss line shape, function, and broadening. So, G new D new is called line shape function. The main reason of the line shape function is why we define that line shape function. The purpose of defining the line shape function is to define the strength of any interaction in the frequency range nu to nu plus d nu. Uh, so this line, the shape function implies that energy levels have with an atoms can interact with radiation over a range of frequency, but the strength of the interaction is a function of frequency. That a particular frequency only, the interaction will be much more than the other frequency. And as you have seen in the lecture, that we know we know the relation between nu and omega. So g nu d nu can be interchanged, g omega d omega and all. And we also know spectral density, which can also be written as a function. And one in particular aspect of line shape function is g nu d nu is equal to 1 if we integrate over 0 to infinity. That if we take frequency range from 0 to infinity, the it actually says the probability of a interaction at certain frequency, or you can say g omega d omega. So integration over the g omega d omega from 0 to infinity means that when frequency range varies from 0 to infinity, what will be the integration, or what will be the probability that a interaction happens. So we know that when frequency range is from 0 to infinity, at any frequency, or the interaction will happen. So whether it at 100 hertz or 100 kilohertz, the interaction is gonna happen. 100 hertz, 100 kilohertz, 100 megahertz, all are fall between 0 to infinity. So that its probability is 1 between 0 to infinity. So from 0 to infinity, g omega d omega will be 1. So here we also know there is another omega dependence term, which is spectral density. uh, as you have seen in the class, that sometimes u omega is greater than g omega, and sometimes u omega is less than g omega. Here it can be shown like this, that u omega is broad. It doesn't mean that value is greater than g omega. It does mean that fw hm of u omega is bigger or wider than g omega. And that compared to g omega, u omega is broad. And this means compared to u omega, g omega is broad. Okay. This is u omega, and this is g omega. Okay. And this can be like shown as, this is u omega, and this is g omega. And depending upon this condition, tau to 1 changes. What is tau to 1? Total number of stimulated emission per unit volume. So tau to 1 will be b to 1, or we can see b u omega into n2. But now we have introduced the concept of line shape function, which is the probability of happening an interaction in the frequency range from nu to nu plus d nu, or omega to omega plus d omega. This can be said omega to omega plus d omega. Okay, but now we have introduced the function line shape function. So we need to include that in that uh, expression and do the mathematics. So B21, we know the expression of B21, N2 is constant, and here it will be U omega, G omega, D omega. Now, the first case, when U omega is broader than G omega, then we know first we need to include the expression of B12. What is the expression of B12? We need to like remind that it is pi square c cube h m naught cube tsp and omega cube. And tsp is equal to 1 by 2 1. So you must have known that from previous classes that it is like a to 1. So that's why I've written tsp. Time TSP is the time for where the population of level 2 reduces 1 by 8th time to population of the previous population of level 2. So tau to 1 when U omega is broader than G omega. Here greater than signs means broader. So with respect to G omega, U omega is broad. So at certain frequency where G omega is varying, the U omega is almost same. 1 minute. Admit. Okay. G omega is between, let's say, omega 1 to omega 2. And you can say that it is almost, let me draw it properly. It is G omega. Okay, sorry. This is omega 1, this is omega 2. And here you can see between omega 1 and omega 2, the U omega. Hello? Is anyone trying to say anything? Okay. So between omega and omega 2, we can say that here it is like this portion. U omega is almost constant. So we can put this U omega term from this expression outside of the integration. So U omega into B1 to G omega D omega. Pi square C cube H squared omega cube. Give me a minute. Sorry guys, give me a minute. System is not working. Solution 2. Okay. Yeah. N 2 pi square c cube h omega cube n naught cube TSP or A21, whatever you want to write, like this, and u omega n2 pi square c cube h n naught cube TSP. It will be like this when u omega is broader than g omega. That is, spectral density is broader than the line shape function. And when u omega is narrower than g omega, then the same concept, that this is g omega to like demonstrate that g omega and u omega is different. I am like drawing u omega left side of the diagram, but u omega, like in this diagram, g omega and u omega can interchange. That can possible, nothing else. This is u omega. So again, from omega, let's say omega 3 to omega 4, you can see that this is the region in g omega. The g omega is constant. So for this, the total number of stimulated emission and unit time will be n2 case 2. N2 is outside of the integration. We can take this. Now g omega is constant, doesn't change over the frequency, where u omega is changing. So the g omega can be taken outside of the integration. Now here it will be pi square c cube h omega cube n naught cube A21 u omega d omega. So into g omega pi square c cube h n naught cube A21, it will be u omega omega cube d omega. Right. So after doing the integration, we can like say what will be the stimulated absorption per unit time per unit volume. So now can go to next part, which is the mechanism for which the broadening happens. So line broadening mechanisms. Line broadening mechanism. So there is when we classified as homogeneous stop sharing. I'm sorry, I'm going to like there is a technical glitch. Sorry. Line broadening mechanism. The mechanism is it's one is homogeneous mechanism, and another is inhomogeneous mechanism, or we can say homogeneous broadening and inhomogeneous broadening. So homogeneous broadening is like the examples of homogeneous broadening is natural broadening or collisional broadening. Doppler broadening falls in the category of inhomogeneous broadening. So why natural broadening? Natural broadening is the reason is the natural reason that the line width of any at any frequency is not zero. So how can we calculate natural broadening? See, can say that ET electric field is E0 e to the power I omega naught t e to the power I minus t by 2 tsp. This is electric field associated to the spontaneous radiation. So it's in the time domain. To go to frequency domain, we need to convert it by Fourier transform. So it will be gone to frequency domain. So it E omega will be 0 to infinity et e to the power minus I omega t dt. One can put here 1 by root over 2 pi or root over 2 pi, whatever, in which way they do Fourier transform. But we are not here bothered about that 1 by 2 pi or 2 root over 2 pi. So E omega will become E0 1 by 2 TSP plus I omega minus omega naught. It is there will be step between these things, so it will be the final result after the integration. So from this, with an intensity of I omega will be E omega whole square. So we may write that line shape function is k into 1 omega minus omega naught whole square plus 1 by 4 TSP whole square. That I omega will be a square of this thing. So line shape function will be the form of this. Now we need to determine the value of k. So we know the normalization function is g omega d omega is 1. So if we do that normalization over 0 to infinity g omega d omega is equal to 1, we will get k is equal to 1 by 2 pi tsp. So g omega we can written as 2 tsp pi into 1 by 4 omega minus omega naught whole square. Omega naught is the central frequency. Square. So this function can be written as a Lorentzian function like this. So this function's FWHM full width hat maxima, which is okay. The FWHM, or we can say delta omega 1, is delta omega 1 by TSP from the Lorentzian changes. So this is that delta omega 1 is the broadening, the width of the broadening due to natural reason. That naturally what will be the broadening of any frequency spectrum. So here there is an example. The spontaneous lifetime of the sodium level leading to D1 is 16 nanosecond. So what will be the natural line width? Can say that the spontaneous lifetime of the sodium level leading to T1 line, the lambda is given 589.1 nanometer is 16 nanosecond. So what is the natural line width? So we know delta omega n is equal to TSP. So from that we can delta mu n is equal to 1 by 2 pi TSP. By putting this value, we get delta nu n is equal to almost 10 megahertz. So this delta nu 1 corresponding to delta lambda of about 0.001 nanometer. Okay. Now we will see this thing in the light of quantum mechanics. Okay. So we know in the admit. Okay. So can say how can we treat natural emission line width as deducted by quantum mechanics. Okay. So we know that uncertainty principle delta E dot delta T is of the order of h cut. Okay. So E assume there is two energy level. Okay. This is U and this is L. So the energy level is not like a single line. The energy varies. Okay, that's why I have drawn a breadth, right? So this variance is like this, and here this variance is like this. Okay, can say it is delta EU and it is delta EL. This is the quantum mechanical description. Okay, so if when the energy level gets broadened, when there is only two state, we know that energy there is a transition from upper level, so it's U, it L. So only one frequency. The line width concept comes from that when will be two discrete energy level, there will be a one frequency. But here there is no two discrete energy level. There is a broadening between in the energy level. So transition can happen like this. Transition can happen like this. Mid to mid, like this. Upper to mid. So when the energy levels get broadened by any reason, that's another topic, how energy level get broadened. It's in the solid state mechanics, and anyway by quantum mechanics you can also like say what are the mechanism. But the point is, we know in here frequency is basically simple. U E energy level U L H cut. But here, when there is a broadening in the energy bandwidth at itself, so how can we get only one frequency between the transition between these two levels? So that's why we can see that the energy levels get broadened, and when energy levels get broadened, there will be associated delta t also. So let us assume that for u level, delta E, we can write delta EU, and there is associated delta T, whichever given name, tau is given the name tau U. Now, we know from the uncertainty principle delta U into tau U will be h cut, or we can say h cut by tau mu. So 1 by tau mu we can write gamma u, or similarly for energy level delta EL, it can be written as h cut gamma L, which will be h cut absorption level gamma L. Okay, so delta ET, total effective energy width, will be delta EU plus delta EL, which will be h cut gamma U plus gamma L. So we already seen that 1 by TSP, spontaneous emission lifetime, where the um, energy drops by 1 by eth time, number of uh, particle in a certain level is given by A to 1 is 1 by 1 TSP. So here gamma U is also 1 by some time for 1 delta TU, or we can say 1 by tau U, and gamma L is equal to 1 by tau L. So we can write this as a, let's see the name UI, from uth level to ith level, and here we use a summation because there is a band, there is a, we can see it is a not a discrete energy level, it's a bandwidth. So from u to join the call, admit. Okay, okay. So if there is a only one transition component or only one transition probability, we will not be needing the summation sign. But here I have already explained to you that from U level to ith level, there will be multiple type of transition probability, and we need to take account all of this transition probability. So here we use the summation sign. So similarly, it will be a L. We can also write is I, or we can say that is J. This is U, I, L, J, all are dummy indices. You can change whatever you like. Okay. So delta E T becomes delta E U. On one thing, the uncertainty, it's a basic rule. They never got minus. Like delta nu should be EU minus delta EL by h cut, right? Because omega frequency is E2 minus E1 by h cut. So why we are adding delta EU and delta EL, not uh, subtract? Because uncertainty never gets reduced. It is always addition. That's why it's the basic rule. dimension analysis, the uncertainty never get subtracted. So that's why we are adding this delta EU plus delta EL. So it will be H cut gamma U plus gamma L, or we can say H cut A U I, and the summation is over I plus J L A L J. So here also summation over I, because I can change, I can vary. Let's say the upper level can be say L1 and lower level can L2. So I can vary, I can vary between in those two line. Okay. So that can be written as H cut. Okay. Now this thing is H cut to omega, where there cannot be any variation in H cut. So uncertainty will automatically shift to omega, or omega UL. Okay, right. So H cut omega UL, sorry, delta, what we have obtained is H cut. Okay, so H cut will get cancelled. So we'll get this is equal to A I plus J A L J. Okay, this is in terms of omega. Now we can write in terms of nu also. So nu is nothing else divided by 2 pi. So this expression is the same thing of this expression, right? 1 by TSP, we can write it 1 to 1, okay, or 2 1. But here we are discussing these things in terms of classical mechanics. So in quantum mechanics, we have already taken into the account that there is a width in the energy states. So we get this expression. This expression will look like that it is different from the classical expression, but it is same as that. Now we can go into another broadening mechanism like collision broadening. So when did the collision broadening happens? So when an atom which is emitting radiation which collides with another atom, like this atom, they are moving in this direction, like this. In this position, say t is equal to 0 position, they are far apart, so their energy levels are not perturbed by each other. So their oscillation is almost sinusoidal energy oscillation, you can say that. Okay. So the radiation emitted is almost sinusoidal because there is no perturbation in those energy levels. But at T is equal to T1, when those atoms are atom 1, atom 2 are in this proximity, so they perturb each other energy level, and because of this, frequency of emission changes, and for that reason broadening happens. This all the broadening mechanism is somehow, the collision broadening is the because of collision, natural broadening because of the natural reasons. Broadening happens in the frequency spectrum. That's the main thing. For you will say that for Doppler reason there is Doppler broadening. There are another kinds of broadening reason, like sometimes the broadening because of the isotopes, because of the amorphous crystal there will be broadening, like that. So here, so this when they are in the close proximity, they influencing each other's energy levels, and for that reason their frequency of emission also changes, and that is the main mechanism of collision broadening. um, Collision broadening, we need to know first what is the collision time. So delta tau c, which is distance by thermal velocity. So the collision time here is very small compared to the time between collision, and hence the collision can be taken as an almost instantaneous collision, and the time is random. So because of collision, sometimes the phase changes. Those- The atoms were having like this kind of sinusoidal emission, but here the collision happens, then we get this, like this, that can happen due to collision. So when this collision happens, the frequency is no longer monochromatic frequency. Okay, that it has now a broadening. So here electric field can be written as I omega naught t plus phi. Here we have taken the phi into account, that I have mentioned that there is a probability of phase change. So again we need to a Fourier transform, and we get this 1 by 2 pi e0 e to the power I omega naught t plus phi e to the power minus I omega t dt. Then we will get I omega, which is of e omega whole square. Okay, so I omega will be the form e0 plus pi whole square, something sinc function is whole square, like that, by omega minus omega naught whole square. Okay, so uh, from also here also we took into account the probability that atom will suffer a collision. Okay, so the probability is given by tau c d tau c of 1 by tau naught into e to the power minus tau naught by tau c by tau naught d tau. So this is the probability that a collision can happen in the interval between tau c to tau c plus d tau c. Okay. So again in the same concept, like line shape function concept, that from 0 to omega the probability of interaction in any particular probability of interaction is 1. It can happen in omega frequency omega 1 or in the frequency omega 2, but in the whole range the probability of interaction happens in is 1, same as the probability for the collision, that for 0 to infinite time there will be a collision between two atoms or more than two atoms. There is no denying. So we can write p tau c d tau c equal to 1. Okay, and tau c p tau c d tau c 0 to infinite can be written as tau naught. Correct. So g omega line shape is not only proportional to I omega now. There is a we need to take in account probability of collision term d tau c and their integration. So after doing this, g omega will be e0 by pi whole square half of 1 omega minus omega naught whole square plus 1 by tau naught whole square. So g omega will be tau naught by 1 plus omega minus omega naught square tau square d omega. So here we can see the FWHM will be 2 by tau naught. So if the mean collision time t tau naught is of 10 to the power minus 6 second, then delta nu, which will be delta omega c by 2 pi, will be of 0.3 megahertz. Okay. And from the kinetic theory of the gases, here I am considering only the kinetic theory of gas, because that give us a collision time tau naught is 1 by 8 pi 2 by 3 to the power half m kb t to the power half p is square. Okay, here m you all know is atomic mass, kb is a Boltzmann's constant, and p is pressure. Kinetic theory of gases. From this we can get this. Okay. So Here is an example like how what kind of question may come. Like in a helium neon laser, pressure of gas is typically 0.5 torr. Okay. If we assume A, okay, here I have Boltzmann constant. We forget to mention what is A. A is the radius or diameter. Okay, let me check. Yeah, radius of the atom. So, one minute, guys. PowerPoint is not working. Okay. This is typically 0.5 torr. We have assumed that A is zero point 0.1 nanometer, T is 300 Kelvin, M is 20 into 1.67 into 10 to the power minus 27 kg. So, what will be the collision broadening? Okay, so from this expression, let me write it like this. From this expansion, and kb will be the given. Okay, what will be the kb? So kb Boltzmann constant will be given. So if what is the collision broadening? Okay, so first you need to calculate collision broadening is collision broadening is 2 by t naught or tau naught. So you have given the expression of tau naught. You need to put everything in this expression, and we need to take into the account the units. We need to be very careful about the units. Please wait 1 minute. There is some condition. To the power half p square. We know p, we know a, we know m, we know t, and we know kb. But all need to put in the equation in correct, in same, not correct, same unit, like either it is CGS or MKS or SI, whatever. We will get T naught is equal to 580 nanosecond, and W collision will be 2 by 580 into 10 to the power minus 9 hertz. So 0.5 into 10 to the power minus 6 hertz, 0.58. It is almost 4, a little less than 4, almost, into 10 to the power 6 hertz. So it is in megahertz range. Okay. So in the presence, it should not be assumed that in the presence of collision broadening there will not be a natural broadening or that case. So in presence of collision broadening, there can be a natural broadening. Then the broadening MWHM will be 1 by TSP plus by 2 T naught. This is for natural broadening. This is collision broadening. Okay. Okay, there are kind of another kind of broadening, that amorphous crystal broadening. Okay. So uh, each of the glass molecules can have slightly different energy levels depending upon the strains that are placed upon them in the matrix. So these correspond to different energy levels of excited state and various kind of different radiating frequencies from different regions. So this give rise to amorphous crystal broadening. I do want to like only mention that and not get into much deeper in this thing. So it can be inhomogeneous most of the time. The Gaussian shape is inhomogeneously broader, and for pure crystalline material, the broadening is not that compared to the amorphous material. So let's move to the next thing, which is Doppler broadening. Okay, so we know the Doppler effect. That Doppler effect is correspond associated to sound waves, such as when a train when a train is like coming to us, and we heard the sound is in higher frequency, then it changes to lower frequency. So it's like from lower frequency to higher frequency, then again to lower frequency, like that. So the shape also it is a characteristic of light waves, and from the Doppler effect we can like measure the distance of the stars from the earth. So because of this thing, also the Doppler effect, there is a broadening caused because of the Doppler effect. So this is called Doppler broadening. So as we have seen that the broadening term, or we are interested in the FWHM, and that we are obtaining from G omega, right? So here also we will follow that suit. So we know Doppler frequency is omega 1 minus V by C inverse. Okay. And we are assuming that radiation is propagating only in one direction. For the simplicity of this thing, radiation can and will and always propagate in all the three direction. For the simplicity of the case, we are um, only like taking into account the z direction, and that if the interaction is so strong, uh, that what do I mean by interaction, that here for Doppler broadening we are considering that frequency omega is passing through a collection of atoms which have a resonant frequency and which move randomly. Here we are neglecting the natural collision and natural broadening and collision broadening in discussion when we are deriving this kind of equation, but those things happen simultaneously. It's not like that collision broadening is happening so that Doppler broadening will not happen. Every kind of broadening for like crystal, the amorphous crystal, there will be amorphous crystal broadening. So all the broadening is going to take place at the same time. For the simplicity of the cases, we only assume that one broadening at one time for the simplicity of the calculation, and also we are only interested in the z direction, and also we are also assuming that there is a strong interaction. Okay, so that we can write this. Okay, as we all know that if we don't assume that there is a strong interaction, then we have several other binomial term. Okay, so what will be the next? Also here will be an probability like the collision. So there will be a term, probability term, that the probability that an atom has a z component of velocity lying between vz to vz plus dz given by Maxwell distribution, that that will take part into the Doppler effect. Okay, so the Maxwell, according to Maxwell distribution, it will be m 2 pi kbt, this is also half, an exponential m vz by 2 kbt into dvz. Okay, so we assume that vz is the velocity of the atom in the z direction, of the z component of the velocity. So it lies between vz to vz plus dvz. So g omega d omega will be c omega naught. We have already seen the relation. G omega will be I omega into P Vz dVz 0 to infinity in the z direction. So it all will be here, m 2 pi k b t to the power half exponential minus m vz square 2 kb d dv vz. So we need to change, like we need to change vz's in the terms of omega, otherwise there will not be possible to have this integration. So I have written this in an incorrect way. So vz needs to be changed to omega domain. So it will be omega minus omega naught by omega naught into c. Okay, the velocity. So g omega d omega is equal to c by omega naught m 2 pi kbt to the power half exponential minus mc square 2 kb t omega minus omega naught square omega naught square into d omega. Okay, from that we can go to the FWHM of the line shape function, which will be 2 omega naught 2 kb t mc square ln 2. Okay, and this is Gaussian function. You can like know from this expression the Gaussian function. Okay, so if we want to write g omega t omega in terms of delta omega d, it will be minus 4 ln 2 omega minus omega naught whole square by delta omega d whole square d omega. Okay, so In the first natural broadening procedure, I said that this is a Lorentzian function. The function will look like a Lorentzian, but here I am saying which is Gaussian. So both of them can look like similar if we see them differently, but like there is a difference. Gaussian is like bell-shaped function. Lorentzian is a bit steeper. So move to the next thing, that we can obtain the lines shape function in the presence of both natural and Doppler broadening. Okay. Hello. Yeah. Uh, okay. I didn't want to go into that deeper because that is out of the scope of this course. That that's why I didn't explain that much. And also their mathematics will be like more complex. I just mentioned that there is I will mention another kind of broadening mechanism so that you don't think that only there is only three kind of mechanism, that's why broadening happen. Broadening is happen because of any kind of reason, like not any kind of reason, like broadening because of the frequency is not monochromatic. So natural broadening, collision broadening, and Doppler broadening are the main thing that contribute to the line shape function broadening, but there are another kind of reasons that can also contribute to the broadening. That's why I mentioned that there is another thing, that amorphous broadening, which you can like think almost because of collisions between their crystal structure. I will also mention different kind of broadening and like let you give the perspective. First, I want to like finish this example. Okay. Okay. Mm, right. Where you are. Obtain the line shape function in the presence of both natural and Doppler broadening. Okay. So, from Maxwell's velocity distribution, the fraction of atoms with the central frequency between omega dash and d omega dash is given by. Now, what happened? It's like this. Exponential minus mc square by 2 kbt omega dash minus omega naught whole square omega naught whole square d omega dash. Okay. And the atoms which characterized in the natural broadening is TSP by pi 1 plus omega minus omega dash whole square 4 TSP whole square. Like I have mentioned already. What is that? Yeah, like this. This corresponds to natural broadening. Okay. And for like velocity distribution, Doppler effect is due to the distribution velocity, and this is so we need to take in account the velocity distribution. So line shape function will be f omega dash d omega into h d omega dash into h omega minus omega dash. Okay, so this corresponds to natural broadening, and this Maxwell distribution comes from Doppler broadening. Okay, so this expression is only convolution. Don't worry about the thing what is convolution and thing. I'm just mentioning this. We can like obtain by convolution method, which is also the out of the scope of this level of course. Okay, so now I want to like draw some pictures. The what would be the shape of Doppler broadened emission line? Okay, so overall shape is like this, but there is like different time. This corresponds to when the frequency is moving toward the observer. Here observer is not person, like it's like atom. So when the atom is traveling towards a fixed atom, so we can say the fixed atom is one atom is observer and another atom is traveling. So when the traveling atom is going towards the observer, or in this position it is away from the observer, and it is the central position. So overall spectrum is this thing travels. So at the center it is like highest amplitude in terms of uh, at this frequency, but when it's also going away from the observer, here observer is also atom, I am mentioning it again and again, that one atom and another atom, so again frequency drops, and total overall Doppler profile is this. So I want to give you some numbers. Okay, say what is the numbers that you can say that the what is the amount of natural broadening and what is the amount of Doppler broadening. So Doppler versus natural broadening. So laser, let's say helium neon laser. So natural broadening And this is Doppler broadening. All are in hertz. So it's lambda helium neon laser 632.8 nanometer. Frequency is almost 0.012. Okay. So Doppler broadening is 1.5 into 10 to the power 9. Natural broadening is 1.4 into 10 to the power 7. For argon laser, again, all the values are in hertz. Okay, this value is 4.5 into 10 to the power 8. This value is 2.7 into 10 to the power 9. This cadmium. Okay, this lambda for argon is 488 nanometer. This is for cadmium. Actually, cadmium laser is using helium cadmium laser. By the way, I want to mention that this helium cadmium laser, argon ion laser, like they are very classical lasers, but uh, they are also well-known lasers. But some these are not like very modern lasers. Now people use for application fiber-based laser, DFB laser, solid state laser, this kind of laser. And helium neon laser, people generally use is that as a pump laser nowadays. Uh, the laser which are being used in everyday life, uh, these are not those kind of laser. Okay, cadmium has lambda is 1.6 nanometer. To the power 7, and it is 2 point, okay, 1.1 into 10 to the power 9. Another laser is medium, is copper, and for that lambda is 510.5. So it is if around 3.6 into 10 to the power 5. And it is of the order of the power 3 into 10 to the power 9. So let us see that for argon laser, the natural broadening is of the order of 10 to the power 8, and the Doppler broadening is order of 10 to the power 9. So when you add those things, for some examples, like when there is also natural broadening and Doppler broadening, when you those add those things and take in account, then you cannot ignore natural broadening. Okay, you cannot ignore that. You need to take it into account when you are like discussing the broadening effects. But for copper, it is of the 10 to the power 5, and it is of the order of 10 to the power 9. Like you can neglect the natural broadening there. Their Doppler broadening dominates the natural broadening by significant amount. You can, when doing the calculation, you can like ignore natural broadening. That's why I wanted to mm, like it's not like you need to remember all those things just for the like for later application. You can take remember that for some laser system natural broadening cannot be ignored, and for some laser application it can be ignored. Okay, there is an example like neodymium doped YAG. So YAG is a material, yttrium, aluminium, garnet. So, so it is said YAG, and another laser is glass laser, doped in YAG and in glass. Okay, so this is crystalline, this is amorphous. Okay, so the broadening in YAG will be much smaller than in glass, because the amorphous structure will also cause one kind of extra broadening. So there is a number that line width is of order 120 gigahertz for ne- neodymium doped YAG. The doping is written like that. Nowadays, titanium doped sapphire gain medium is used, so it is written like this. But the line width for the glass, neodymium doped glass, is almost 5400 gigahertz. It's not like example, it is like information. Okay. Oh, please wait a minute. Huh? What is the output of wavelength of the YAG laser? Okay, let me check. I don't remember that, but I can check. And like, as I have mentioned, the system I'm working, it's nothing to do with YAG, so I don't like remember it all the time. But I can tell you. Okay. Oh, okay. It is of 1064 nanometer. Current state of the art NDX system has 1064 nanometer. But nowadays it starts with that. But from that we can generate different kind of frequency, like for non using nonlinear crystal. Uh, I don't want to go into that thing. Because of nonlinearity in the crystal, you can generate like if this is a nonlinear crystal, a nonlinear crystal has a different refractive index in different direction. That's the reason that we can generate different frequency from that. That if we put omega, we can get 2 omega. If we put omega 1 and omega 2, we can get 2 omega 1, 2 omega 2, omega 1 plus omega 2, omega 1 minus omega 2. So when we discuss nonlinearity of a crystal, we always discuss in the terms of frequency. So from this 1064 nanometer, we can generate 532 nanometer in that NDAC laser system itself. Okay, 532, another less than that, 250-ish nanometer, like that. Admit. So this non-linearity is not the scope of this course. I am just mentioning that you asked what is the output of the wavelength, that's 1064 nanometer. So from that we can get 532 nanometer, 266 nanometer. This is because of using the non-linearity of this thing. And also, like mathematically minus 2 omega minus 2 omega 2 also like present when you do calculation electromagnetically, but they are not like, you also know, minus 2 omega minus 2 omega 2, they are not like actual frequency, they means another things, and that I cannot discuss here, like it will take another course and another class. So you can say that 1064 nanometer is the output of the NDAC laser. Okay. Yeah. Compared to? Yeah. Compared to UV laser, NDAC laser, what, I didn't get it. Okay, I can discuss those things. Yeah, yeah, I can discuss, like let me get into those thing and tell you in the next class. Uh, okay, that is not on the top of my mind at now. Hmm. Waiting to like, okay, this looks messy. Oh, my PowerPoint to response, because quickly I want to mention another kind of broadening. Just mention this. Mhm. So there is another kind of broadening due to isotope effects. So it will determine the frequency shifts due to the more than one isotope of a particular atom. Different isotopes have different uh, and isotope of same material has different kind of abundance, and they have atoms having the same number of protons and electrons but with different number of neutrons. So like in helium, helium 4 and helium 3. Helium 4 is in abundance like helium 4. This is 2 neutron. It is 99%. Helium 3, 1 neutron. It is almost less than 1%. Okay. 0.0013%. Same for neon. So this slightly different number of neutrons within their nuclei exhibits different level of energy levels. And when the energy levels get different, the frequency due to emission will also get different. And that's why, because of the presence of different kind of isotope, there is also a broadening. Basically, these isotopes, like, let me write, because of isotopes, two-way energy shifts. One is mass effect. Okay. And another is volume effect. So when the isotope changes, the like one has two neutron, another is one neutron. The neutrons are not massless; they are not photons, which are massless. The neutron is not massless, so there is a mass difference. And also, neutron is also has a volume, so there will be more volume in the heavier variety of isotopes. So this affects the shifts. So because the number of s electrons is different in these two levels, and also there are the kind of things. So basically for these two reasons the energy level shifts, and when the shifts, like it's not like from 1 nanometer to 2 nanometer, it's maybe in the order of 10 to the power 15 meter, but and energy shifts, and that's why also frequency shift, and that's why also broadening happens. So all this discussion about broadening is basically with one intention, is that there is nothing like a this kind of frequency, like there is no spectrum like this. Like if you have a good enough resolution, you will always see like this. There is always a width, and that for this width there is logical reason, which is like natural broadening, that will be natural cause, natural broadening, the Doppler broadening, and the one thing I also the collision broadening, and another kind of broadening that like isotope broadening, uh, amorphous crystallized broadening. And sometimes the energy level shift another reasons, like upper energy level shifts for different reason, only lower energy level shifts. So sometimes I don't, the from these two energy level, also another thing, for some reason the relaxation time, let us say this is one T1, this is T2, and three level system, relaxation time T1 varies. So when T1 varies, also we have see the delta omega here is 2 or 1 or something. The lower part has always a time factor. When the relaxation time varies, also the broadening varies. So between these so natural broadening, Doppler broadening, collision broadening, isotope broadening, there is another kind, different kinds of broadening, but that is not the scope of this course. I just want to mention of all this. For the course, you just need to focus on those three kind of broadening. So I think that's for all today, and I'll upload the video and also the like slides. And also one thing, I saw that the first assignment date is till 9th of August. So I didn't discuss the first assignment. And also I have seen that second assignment submission date also 9th August. So I hope I'll discuss this assignment in the next class. Thank you. What? Okay, okay. Thank you. Okay, thank you.